Hello, NDC Porto. I'm so glad that so many turned up on my little talk about crazy things to do in JavaScript. So my talk is called You Can't Do That with JavaScript, and the subtitle is Wasting Time While Having Fun, and that is essentially what this little projects that I've been doing are. But before we get into that, let me just do a little slide about myself. So my name is Espen Sande-Larsen. I worked as a developer and a tech lead in several different roles for the soon-to-be 30 years, believe it or not. I'm also a musician. I release and I play music professionally sometimes. I have 3 kids that I adore, and I am passionate and deeply, deeply interested in anything technological, be it making things with hardware or software or whatever. And when I can't do these crazy part-time projects, I really enjoy drinking beer and having fun tech conversation with like-minded individuals. And I work for this little thing called DNB Bank up in Norway. I work in a division called New Tech Lab, which is kind of this innovation lab where we get to play and tinker with technologies and cutting-edge stuff, which is pretty cool. And you may notice that something is missing from this slide, because usually in talks like these, when people present this slide, they list up something that is not in my slide, and that is their academic accolades. So it's where they went to school, what degrees they have, the PhDs they have. I don't have any of that, because I dropped out of high school when I was 16, and I started working. Well, the truth was I didn't really drop out. I was kind of voted out by the teachers, so we both decided school wasn't for me. But I saw that as an advantage, because it meant I could just start working and getting paid for doing stuff. And when I was 16, I learned 2 things, that there are 2 things that they will pay me to do. One is performing music, and the other one is writing software. And you may ask yourself, how on earth does a 16-year-old kid manage to drum up a career in software development without going to school or anything like that? And it all started with this thing, back when I was an even younger kid. Some of you have seen this before, some of you have not. This is a Commodore 64 that we got when my brother brought that into our house. He came running into the room and shouted my name because he was so excited that I had gotten this thing. He had traded some drugs for it, so I call that the drug deal of the century, because we got a computer and they got some drugs, and ever since that day I've been hooked on computing and not drugs. And that thing was, and when you buy a black market computer, you don't really get the best support package, so it didn't come with any books or manuals or software or anything. It came with the box, the power cable, and the RF cable to hook it up to the TV. So we turned it on, and it was this blue screen that blinked and said ready, and then we didn't understand a thing after that. And we would spend the better part of the next years learning how that machine worked and getting that machine to do stuff. I remember the first time I found a book in my school's library. It's 25 games for the Commodore 64, which was the actual source code for those games in book form, because back in the 80s, distributing software by paper was a sound strategy. There was also only one problem, because the typeset of the offset printer used to print the books was not necessarily compatible with the characters on the keyboard of the Commodore 64. So these programs usually had some bugs or some issues with them. That is hard to debug when it's a character that's not present on your computer that's wrong. And I would use days and nights and weekends and all my spare time trying to figure out and get that thing to work. And I do remember the intense feeling of accomplishment when that first game actually ran and what I had put into the computer actually appeared on the screen. That got me hooked on making software. And I've been doing that ever since. And after, when I got a bit older, I got into something called the Demoscene. Any of you familiar with the Demoscene? Some of you, okay. For those uninitiated, Demoscene was this thing mostly prevalent back in the 80s and 90s. It's still a thing, but it isn't as extensive nowadays. Where you would bring your computer into these big rooms with your friends, and you would all sit around coding up things called demos, which are these graphical presentations or animations and effects and sound and music. And you would compete against all the other ones who could make the most impressive one. And you had some constraints. You had a limited amount of program space that your program had to fit in. It was like there was like these classes like 2K or 4K or 16K, 32K, and so on. And that meant that your entire program, if you competed in the 4K, it had to fit into 4K bytes, no more. And programming these limited machines and resources kind of gets you into a different mode of developing, rather than when you're doing this form of development, other than when you're doing enterprise software. Because you don't have the luxury of nice abstractions or design patterns or stuff like that. It's all about cramming out as much of those bytes as possible. So whatever bytes you can save, whatever instructions you can shave off your program, you do so. And you can commit every programming crime known to man in order to achieve that. And the only requirement you have is to have to create the most awesomeness possible because you want to win the competition. That means you're putting in extreme efforts for small, tiny improvements. And it's quite a thing. And it's really interesting to do these things. And when you're doing this with your friends, it kind of puts you in this like rapid cycling of your ego, because you're swaying back and front from feeling like the most awesome developer who ever lived to the biggest idiot that ever existed in the scope of an instant. And this environment was extremely competitive. It was basically like doing sports. This was kind of like the Olympics for us. And it's fun as F triple star because it's really, really cool. I never actually won anything or something like that, but I did compete, and here are some examples of things that I did. So these are some classical effects, as you can see, that I've been doing. So, but then I started working. I left the Demoscene stuff, and I learned that when you're doing software for work and you're getting paid for it, it's much more boring than when you're doing it for fun and trying to impress your friends. So even though I thought it was cool that I could get paid for writing software, I got bored. And when I get bored, I start to tinker with things and start what I like to call crazy projects. And crazy projects are projects I give myself to do in my spare time where I have some kind of constraints that I have to fit and finish the project within. And these can get quite extensive, and they're not necessarily just in JavaScript. They can be hardware or software or anything. For instance, I told myself, you have a weekend to build an arcade machine. You're not allowed to buy any parts, so I did that. This is my daughter. She really loved it so much, she wanted it in her bed. I said yes, her mom said no, so that didn't happen. Now it's at my office. I built a $40 million supercomputer from the 90s I got shipped to me in boxes. I didn't pay 40 million for it. I paid 50 euros for it. But I had to put that thing together, restore it, fix all the problems with it, and got it running. That's a Silicon Graphics Origin 2800 machine. And it's horribly inconvenient to have in your house. It's not feasible to use for anything. And when you power it on, it sounds like a jet engine. And when you hook it up to your power grid, it draws 100 amps. So it's not the most practical computer to have in your house. And this is one of my craziest projects that I'm kind of known for. If you notice on the left, there's a box of eggs. And there's this machine holding an egg, and there's a pen above the egg. And that's how I got my current job at DNB Bank, because I saw the ad for my position. I thought it was very, very interesting, so I thought I need to apply for that job, but no school, no degrees, so I have to figure out how to get on top of the application pile. So I had to think. And I thought, if my application is in 3 dimensions, it's pretty hard to put it on the bottom of something if it's round. So I thought, I'll write my application on an egg and send the egg. So I created this robot. This seemed as a good idea at the time, so I started building this robot, 3D printed the parts, wrote the firmware, wrote the drivers. I got it writing on the eggs pretty good, because it's actually non-trivial to project 2D Cartesian coordinates onto an egg-shaped surface. One thing if it was spherical, but it's egg-shaped. But I got it decent enough so we can read the text of the egg. So I sent, and this is now 5 a.m. in the night, and I thought, well, I better sanity check this before I send it in. So there's 2 people in the world I can contact at 5 a.m. One is my nephew, who lives in the US. He's a tech startup guy. And the other one is my mother, because she doesn't sleep just like me. And, and my nephew said, that's cool. And my mom said, you should never show this to anyone, because nobody will speak to you again, and they will think you are insane. So I thought, good, I'll send it in. So I sent it in, and I got the job. So it evidently worked. And lately, the last couple of years, 6 or 7 years, I've been tinkering with JavaScript in this project. And you may ask yourself, why JavaScript? You're a .NET guy, you're a C++ guy. Well, I find JavaScript quite interesting because it's sometimes silly and quirky and has some really special idiosyncrasies, some of which can bite you when you least expect it, and that makes it interesting. And everybody seems to hate it for some reason. Whenever people speak about JavaScript, they always say, oh, I hate JavaScript, it's awful. I love TypeScript, but I hate JavaScript. But even though people hate it, it's used everywhere. People are using this server-side, client-side. They're making everything in JavaScript these days. I even found on my way to the conference that someone had written a static binary compiler for JavaScript, meaning you can compile to real native binaries from JavaScript. Gives me a couple of ideas for some future projects. But yeah. So it seems to be taking over the world. So I thought, what can I do with this thing? What can I do with JavaScript? So I sat at the lunchroom at work one day, and I started pitching these ideas for a new crazy project I could take on. So I said, what about we make an operating system in JavaScript? Of course, people would reply, you're crazy. You can't do that with JavaScript, because it's not tuned to do so. And how about if I write a hardware emulator? Maybe I can write a Nintendo emulator or something like that in JavaScript. Again, they say you can't do that with JavaScript. It's not feasible. It's not for performance-critical tasks. So I thought, what about games? Can I make some games? No, you can't do that with JavaScript. You can make some simple, silly games for displaying on a web page, but you can't make real immersive games. And then I thought, what about my graphic demos from my Demoscene days? Surely we can make that in JavaScript. They say, no, you can't do graphics. It's not what it's intended to do. You can make buttons and stuff, but you can't make graphics. And I thought, 3D graphics? No can do. So when everybody told me they can't do that in JavaScript, that gave me the idea that maybe I should do it, so I did it. So let me just start by showing you a couple of examples. We're going to start with 2D graphics first before we dive into 3D, because it kind of helps us ease into the material a bit. So this is a very classical effect. It's called flames. It looks like this. The idea is basically you take the shape of the thing you want to burn, take the outline of that shape, and you randomize the pixels that make up that outline between black and white pixels. In this case, the shape is very simple. It's the line on the bottom of the screen. And then you play a bit of Minesweeper game with the pixels up the screen. So the pixel that's there gets the color. That's the average color of the green ones. So you just do that from the bottom and up, and you do that for every frame. You will get this effect. So let's see if the demo gods are with me today. So this is what that looks like. No, that's not what that looks like. I have to stop the presenter view, maybe. There we go. So this is what that looks like. There's a code. You see, I randomized the bottom of the screen, and we do this naive loop where we play that Minesweeper game and give this the average color. And it looks kind of cool. And you can burn any object. It's just the outline that has to be randomized. And it could be text, it could be shapes, it could be anything. So I thought, that's cool. Let's go. This is going to be so if I go back to PowerPoint, will it work? Yeah. And I just have to show presenter view. That's. Now I don't have presenter view. This is a bit of a snag. Ah, there we go. Okay. So I thought, let me do a plasma next. That's a simple effect. It's the effect is basically based that you take some sine waves and you sum them together. They're called sinusoids. You do that for every pixel on your screen, and you save those the amplitudes of the waves. And then you use the amplitude to look up in a palette of colors. And you make it so the palette can cycle from one end to the other. If you shift off a color at the top, you can put it back on the end, and it will seem seamless. And it looks like this when you computed it. So it's pretty cool as well. And if you cycle the colors through every frame, you will get an animation effect. But that's not the waves moving, it's just the colors changing positions. So let's see if this works now. No, so I have to go out, duplicate. OK, this is going to be. OK, so that's the plasma. So it looks like it's moving, but the only thing that's moving, that's the palette up there. And here you can see the generation of the waves in the XY space. And you just sum those two up, and this will create this plasma. There's two sinusoids in this example. And it's a pretty basic staple effects in the Demoscene. It's used all over the place. So this proved to me that I could use the canvas as a frame buffer, and that means that I can implement graphics routines. And if I can do that, that means I can probably do something in more dimensions than 2. So again, this is that's the one. Present the view. OK, this is going to be a bit of a snag. Come on. There we go. And 3D engines are basically, they come in many shapes and forms and sizes. So I decided I will tackle the rasterizer as the first one, because that's probably the simplest one, because that's one of the earliest ones. And a rasterizer, the idea is pretty simple. You have a 3D object in world space, meaning the world that the object resides in. You project that shape onto a 2D plane. That's the screen. That's in screen space. And then you figure out where to put the pixels and what color each pixel should be. That is the rasterizer part. And so I started building this thing. So again, I should not have done that many demos, I guess. OK, so I'm going to get the hang of this. So I started out writing this. I started thinking I need some vectors to define the vertices of this box. And I have those in this structure. And I built up faces. That's the quads that make up the box. I wrote a pretty simple projection of those vectors to try to project it onto the screen. And as you can see, it kind of looks like 3D, but it's also kind of doesn't, because there's a problem there. And the problem is that all the sides are of equal length, regardless of how deep they are in C-space, so there's no perspective. It looks like an IKEA assembly illustration rather than a 3D box. And this had me going down into the rabbit hole that is all of this 3D math stuff. Again, high school dropout, didn't learn this in school, so I had to learn about these vectors and stuff while doing this project. And suddenly I figured out what I could do. So I had to make it so that I have this scaling factor in the projection of the vectors. You can see over here. That factor now takes into account the distance in Z-space and the field of view you're viewing the thing in. And then we get the perspective. That took a night of reading on the internet to figure out. And now I thought, well, we are home free. We have a spinning cube in 3D space, but it's very unimpressive because it's just lines. There's no shading. There's no nothing. And I tried to figure out how do I color that in and shade that in. And I couldn't figure it out because it was pretty difficult. Because whenever I found an approach that seemed to work, there was always some kind of corner case that made it not work in all cases. So I kind of scrapped the idea and started reading a bit more. So let's see if I can go back to my presentation again. Then I needed to go back to the drawing board and started to think a bit more about 3D and how to do stuff. And it turns out I had overlooked one detail, and that is that usually rasterizers work with these things that are triangles and not polygons, because triangles are much easier to draw. But I had to figure out how do I transform these in 3D space and also be able to transform the camera and the world and each object individually.
So I had to figure out how to triangulate my meshes, and I had to figure out how to transform them. And that sent me down another rabbit hole, because that introduced the concept of a matrix. And matrices are these kind of strange black boxes that make sense to some and seem like voodoo to others. And at this point, I'm trying to wrap my head around these things. There's probably like 10 years of mathematics I'm missing in my portfolio to understand all of these things. So I'm reading, and I'm reading textbooks and net forums, and I'm seeing YouTube videos. I'm trying to figure this out. And yeah, it doesn't seem to make sense to me. I'm trying to get all of this down, and suddenly something loosens, and I'm able to wrap my head around it. So I figure out that I need a set of matrices that are used for the basic transformations I need. There's one for rotation, there's one for translation, and there's one for projection. I've finally derived the projection matrix. This is one of my actual notes from this endeavor. And I find out that in order for all of these matrices to work, you may notice that all the vectors in the on the white page here, they don't only have 3 components, they have a 4th component. So we have X, Y, Z, and W. And if you wonder what W stands for, I've figured it out that it has to stand for witchcraft, because that's what it does in my view. It kind of makes things happen. And I code up everything. I checked the math. It seemed to be working, but for some reason it doesn't really work when I program the thing and try to get things on screen. Everything gets distorted and everything gets screwed up. And I'm so sure that the problem is in the mathematics and not with the code, and I'm trying to figure that out. And I'm getting desperate at this point, because now I'm like in 96 hours into this project with minimal amounts of sleep. So I start going to Reddit, to forums, to more YouTube videos, Wolfram Alpha, all the math stuff, and the math seems to be correct. So there has to be something in the code there, and I can't really figure that out. Maybe I'm stupid. I'm banging my head against the wall. I start drinking because maybe I need to hit the Balmer peak, because it's evidently a thing. If you don't know what this is that alcohol concentration actually affects your programming skills, and there's this super sweet spot where you get like super exponentially higher, better at programming from being just a little bit drunk. And at this point, nothing is working. The Balmer peak isn't working. I'm drinking, I'm frustrated, I'm banging my head against my desk. There's paper everywhere. It seems like a scene from A Beautiful Mind. I'm descending into madness. My wife comes down and asks me to come to bed and leave this thing. And I'm like, can't you see? I'm in the matrix. I'm trying to figure out the matrix. I am the matrix. And it's raving like a lunatic. And it turns out the problem isn't the matrix. The maths were correct. I had figured that out. The problem was freaking JavaScript, because JavaScript has a funny way of scoping things. Because most sane programming languages in the world, they have what's known as lexical scoping, meaning that your values and references are scoped to your local class or your local namespace, but not in JavaScript. In JavaScript, everything uses something called a functional scoping, and that means that it's scoped to the closest function. So, for instance, in this example, it's just a silly little function. It's a foo, takes in a bar, returns an object, and if the reason it's cluttered is because there's the right way of doing it and the wrong way. So if you put this bar on this property, and you have this method multiplying that bar with n, in a sane language like C#, if you initiate that, you call that, you will get 10. If you mute the state of bar and you call that again with a new value, you will get 25 because you muted the state. Not in JavaScript. In JavaScript, you can mute the state, but this still sees the original state that it was initialized with. That's because each function closes over a reference to that value, and that's its reference. So this bar and this bar is different, which is hurtful. So I rewrite everything to use a non-mutable pattern, And I finally get that working. I get my transformation matrix up and going, following my derivation. And then we get to this level. Let me see if I can change the view. And now I have a triangulated mesh. I project it into Z-space. And I now have this transformation pipeline where I do rotations first through the matrix. I do translation through the matrix. And I project that mesh onto the screen using the matrix. And now I have like a small library of vectors and matrices. And you may ask yourself, why are you not using a ready-made one? And that is because that's the whole point. I want to learn this thing, and I learned that by making it from scratch. That's also one of the constraints for this project, no libraries. So now we're talking. So now the next thing I have to figure out is how do I color it in? And it turns out that's pretty simple. Because what you do is you take this line and that line. They are 90 degrees to each other, but they exist on the same plane. So you take a point there, and you take the corresponding point on the other side, and you just draw a line across it. And you do that for everything that's inside your triangle, and you do the same thing for the next triangle. And if you draw these lines like this, you end up with a triangle. That's called a scanline renderer. And to get it shaded, what you need to do is you need to calculate what's known as a normal. And that is, if you take the cross product of this vector and that vector, you will get a new vector that's perpendicular to that plane. It looks like this. And then you can take the dot product of a light's position from that normal vector, and that will tell you how aligned those two vectors are. So if they are seeing each other, that will evaluate to 1. But if they are exact opposite of each other, it would be 0. You can use that value to attenuate your color, and then you will get a shading if you just color each polygon with that shade that you have calculated. And it looks like this. And now we have a working rasterizer with an easy flat shading color model. And now it's starting to go somewhere. So now the next thing we need to figure out is what do we do now? And it all goes wrong again. So I'm trying to implement the FPV camera. So if I do WASD, I can move. And it looks kind of good, but you see what happens. Suddenly, something wraps around to the other side. And I won't show you because it will cause the browser to crash. But if I go inside, so things are starting to go behind me, the problems is that I'm in my projection matrix. I'm using the Z value in the scaling factor. I'm dividing by that Z distance. So if the thing is 0 distance away from you, you get the divide by 0. In JavaScript, that doesn't throw. It goes to infinity, meaning I'm trying to draw infinitely large polygons, which causes the browser to be really mad at you. So again, I have to descend into madness and figure out how to fix that. And that is also a pretty easy solution, because what you do is you have to introduce something called clipping. And that means that if that handle goes off that edge, we need to remove everything here that's not part of the scene anymore. And where it intersects the edge, we need to insert new vertices and generate new polygons. That's known as clipping. And you clip against all 6 planes of your screen. So you have like the front plane, that's where the closest thing to your camera. You have the far plane, that's as far as you're willing to project something. And then you have left, right, top, down. And when you do that, let me see, it's this button to go to the next, you will introduce what's known as clipping. And it can be a couple of cases. Either all the vertices of your triangle are inside your clipping box, then it's on screen, so that's fine. Or all 3 vertices of your triangle are outside of your clipping box, well, then you can just ignore it. And then come the interesting cases. That is when just one of them are inside or outside, then you have to put up a new point. So you can see here, you go up a bit. You can see here, and this is a little bit slow for some reason. But if you watch this hill here, you can see that This is what it looks like normally. And as I go closer, you see I've now drawn new triangles. And you can see the points are aligned on the bottom of the screen. And that's clipping. So I'm drawing new triangles. The normal isn't affected because they are in the same plane as the face you are clipping against. So now I have this thing where I can actually move through a landscape. And you can see the clipping happening. That's the red and the green. The red ones are the ones that get 2 new triangles, and the green ones are the ones that get 1 new triangle. And that's the 2 cases you have when you're doing clipping. And so I was really stoked about this. I now had the working rasterizer. So I decided I will show that to the people I work with to see if they were impressed by my JavaScripting efforts. And basically, they were terribly unimpressed. Because all they said was, great, you did a thing. And now you can game like it's 1989, because rasterizing is complicated. And I started hitting up on the performance threshold of what was feasible to do in real time. But math is kind of like a gateway drug, because I thought all the math stuff was really interesting, and I really wanted more. So I thought, well, I cannot possibly fail a second time, so I decided I will build a ray tracer next. And of course, they told me you can't do that in JavaScript. And as I was preparing for this thing, I found this cool book by Peter Shirley and a couple of other contributors. It's called Ray Tracing in 1 Weekend, and it's an excellent book for anybody who wants to learn about how ray tracing works. And if you're on a crazy holiday or weekend project trying to implement the ray tracer in JavaScript, well, it's a good thing to have. All the examples are in C++. It's not JavaScript. But I implemented the C++ one, and that taught me enough in how I could implement this in JavaScript. So ray tracing is pretty simple, because what you're doing is you're modeling how light works in the physical world. So light works by coming from the light source. It travels through space, hits something, it bounces off that something, and eventually it ends up in our eyes. And our brains turn that into an image for us. In ray tracing, you do the same thing, but you do it in the opposite direction, and that is because you don't care about all the rays that never hits your eye. You only care about ones that hit your eye. So you start by your eye or your camera, projected through the pixel at an angle of the pixel, and then if you hit something, you create some new rays and bounce off that thing, and then you can figure out if you're in the light, if you're in the shade, and you can figure out a way to color in that pixel. And that routine that colors the pixel, that's referred to as a shader. So let's see how that worked out. Because my first attempt, I thought I had it, I thought it would work, but I failed miserably once again. So let me see if we should do it like this. So this is the ray tracer. It's running. It's super slow. That's the first thing I noticed. It's slow within the C++ versions as well, but it's a new dimension of slow in the browser. But it's much faster than ray tracing was back when I got into 3D graphics the first time. So this is supposed to be a unit sphere in the center of the screen, 5 units away from the camera. And as you can see, that's not what's happening. And I also needed to tackle the performance problem, because this is slow. Your browser thinks something is running in an eternal loop, and it wants to actually quit the page. And that's not what you want. So I needed to figure out a way to make it more performant. The problem with the projection was easy. That was just me who had derped on when I ported the code over from C++ to JavaScript. I just misplaced a couple of variables, so that was easy. No need to delve into the madness and abyss of problem solving for this one. But I needed to solve the performance issue. So my first thought was, what if I make this into an Azure function or an AWS Lambda? I can send each bits of the screen as a job to that serverless function, and I would just get back a return. And that turned out to be a horrible idea, because the underlying services for the Lambda and the Azure functions turned out to be really, really, really mad at me for doing these CPU-intensive things. And also half of them would fail and never return because they hit some internal timeout threshold and stuff like that, so that was a nightmare. Then somebody told me, why didn't you just use web workers? That's what they are for, right? So I thought, I'll do web workers. And that then made it much faster. So this is how I put it up into web workers. If you know anything about web workers, they are pretty awesome. For those of you who don't, it's basically this thing. If you look at the center one, it's kind of hard to see. Maybe I need to zoom in or something. So you set up a worker by doing a new worker. You can have as many as you want, but it kind of makes sense to have it match your thread count on some level, because otherwise it will be queued up anyways. The cool thing is that the work it does is defer to a background thread, so it doesn't lock your interface. And it works by you setting up a script that the worker is running, and you can have a number of them. So I just have an array of workers, like a thread pool. And how you work with them is you send them a message, and you get a message back once they complete. So this is using the event loop in JavaScript. So we just put an event handler on message. And in this instance, we just get the raw pixel data back. So all I have to do is draw those on the screen. And this is what we send to the worker. So it's just a job of how many rows and columns to generate. And we just tell each job that this is your tile size, this is your column and row, and this is your current pixel, and this is the width and height of the screen you're supposed to do. So you just render out a small portion of the screen. And also, in the ray tracer, I introduced the notion of array. That's an object. It has an origin and a direction, and it can point at something through a method. And we then calculate something called a bounce, because in ray tracers, the fidelity comes from doing multiple random bounces of the objects they hit. And that gives you all of these nice physical properties of lights, because you can use all of those mathematical things that tells things how they look. So we have a bounce. It checks if it hits something. It has the t value, that is the root of the object you hit. Basically, that is solving an equation called the quadratic equation, which has either 0 roots, 1 root, or 2 roots as the answer. That tells you if you're on the surface, inside the surface, or past the surface. You have your normal that we calculated almost the same way as we did in the rasterizer. It's a bit different because we are using ideal surfaces in this instance. And we have the ray that's being projected, and we will have a material that says what is this surface properties. And then we have the shader, that's the color function. Its purpose is just to say what color is this pixel. And then we have the camera, and we have everything else. And that's what's been rendered, and it goes pretty fast. So this is just the linear interpretation of the y-coordinate in y-space between two colors. So it's this scene, so we need to introduce an object. So we introduce the notion of a sphere. So basically, this is the quadratic equation that's solved. You solve for t, and you get back if it's hit or not. And in this case, if we hit it, we will just return pure red as the color, so we will get a red circle. This has two problems. One thing is that we are just looking if something hits the sphere at all. So that means that even if I move that sphere back behind me in space, I can still see it because I can see behind me as well. We will fix that. So the next thing we need to do is figure out the normal, because that's where shading begins. So that is what we do here. And that is just almost the same. So we just calculate a vector that's pointing out of the surface, and on a sphere, that's the formula for that. And if we give the color value based on that normal, we can get this rainbow-colored ball. And that's kind of a hello world in graphics and 3D things, meaning if you have an object that's colored by its own normal, that means you're doing something right. So the next thing we need to do then, now we can start building. Now we can add more things to our shader. So we can calculate what's known as a Libertian, and we can also introduce the notion of having more than one sphere in the scene. So I create a class called a sphere surface. It has a center and a radius. That's what a sphere is. It's every point that's one radii away from its center. We implement that same hit function to ask a sphere if you're hit by this ray. And then we do this thing where if we hit something, we take a new ray that's a random direction away from the point that we did, and we recursively call ourselves and do another calculation, and we attenuate that value by half its value. And we do that over and over again until we hit a threshold, and that will give us this diffuse shading, or Lambertian, as it's called. And the nice thing is that we get the shadows, the soft shadows we get, but you can also see that it's kind of noisy, and that is because in order to get high fidelity in ray tracing, you have to do this for every pixel multiple times for the same pixel, and you average the result every time. And that will give you less noise every time you do it, because what you do is you offset that pixel by a sub-pixel amount, and you get an average, and that reduces noise, which makes it even more CPU intensive. So I've set the samples down for this demonstration in order to keep the fidelity going. But now we can start to implement more types of surfaces, so we can add materials. So next thing is to introduce other types of surfaces, because that was a rough surface, kind of like clay or stone. So now we can do one that's called metal. And again, a surface or a material is just this. It has a base color that's called the albedo. And we have a scatter function that scatters the ray. And it calculates which direction or which property of the scattering that's happening. And metal has reflections, so what we do is we create a reflected ray. That means that the ray will go in the opposite direction. And then we attenuate that by this fuzzing value. And if we follow that ray, we will hit something else, which means that we will see that thing in the mirror image. And that's what you can see here. So we can see the reflection of the pink ball in the gold and the silver ball. And this has more fuzz, so it's a more fuzzy reflection, and this has less fuzz, so it's a less fuzzy reflection. And so that's metals. And we can also create glass by just implementing the same things in one of these materials. So it's a little bit different, because when you're going inside the surface, it's still the same as a reflection, but you go in the opposite direction of the reflection. So it means it gets inverted. And you have to calculate a distortion value, and that is based on something called the index of refraction. And there's this whole branch of physics where they tell you how light behaves inside of mediums or volumes. I'm not going to go into that because, quite honestly, it's beyond my understanding. Again, high school dropout. But what I am going to say is that in computer graphics, it's usual to just use this little cheat or hack that's called Slick approximation by a guy called Slick. And why it works, I don't know, but it works, and that's how you do it. And the silver ball is now a glass ball, so it's maybe hard to see, but this is the ground plane that's inverted, and this is the sky that's inverted, meaning that the rays have entered the volume, been flipped over, and they are scattering to either side. And that's where that book ends, and that's where the Weekend Ray Tracer project ends. And now I actually have a ray tracer implemented in JavaScript. I can extend this with more surfaces, more materials, more lighting models. I can add like specular reflections and stuff like this. But I'm also kind of at the point where the more you add, the slower it gets, because it means more bounces, and more bounces mean less performance. So suddenly you try to add like specular reflections and other kinds of things, and it goes up exponentially for all the features you add. So I left this project here, and I was a bit disappointed that I couldn't take it all the way to an impressive level. But I had another idea. How about I just have to get my presenter view back. So how about I do something called a ray marcher? And a ray marcher is basically kind of the cousin of the ray tracer. You still cast the ray from your eye and through the screen, but what you do is you figure out the distance to all the objects in your scenes, and you march along your ray the shortest one. And you keep doing that in iterations until you hit some delta, and that means you're on a surface, and then you can start your whole shading thing. So it works like this. This is a 2D representation of ray marching. So you start at this point. You check the distance to all the objects. In this case, this is the nearest one. So this distance from this to that, I can march along this direction. That gives me basically a circle. And I can do that again. And it's still this one. So it's this distance. March along the ray again. And now I'm here, so I'm closer to this thing, so I can march that distance. And then I'm on the surface, I can do my calculations. This is live, you can check it out on your phones if you want to. It's just has this ray in a random scene and shows you how it works. And the cool thing about ray marching is that it enables you to use something called distance estimators to your objects, because it's kind of the next thing you have to think about is how do I calculate these distances. And if you use distance estimators, there are something called signed distance functions, where you have an ideal mathematical representation of your object, and it's given a vector, and its object is to just calculate how far is this point from this mathematical object. And it's called signed distance functions because it's signed, meaning it returns either a negative or a positive value. And basically, if it's above 0, your point is outside the object, so there's nothing to do. If it's exactly 0 or near your delta, as small as you want to go, because you will be on the surface, and if it's negative, well, then you're inside the surface. And this gives you some cool ways to combine these things with mathematics, which is pretty nice. And also, your scene is kind of like the function of everything mathematically, so that's kind of nice. So you're not working with polygons anymore. And let's see what that looks like. So I started implementing ray marcher. I have done this before back in my Demoscene days, because that's one of the ways we got some cool effects. And this is how I did it in JavaScript. So this is a ray marcher. I still use the web workers because the performance is still bad. So let's go into this thing. So we have this thing called render pixel that calls this ray marching function. It has an origin and a direction it's going to march in. And this ray marching function, it takes the origin and the direction, and if it starts a loop, it's going to either break if you're on a surface or you exceed the max distance, or if you've exhausted all the times you're willing to go through this loop. So we have these are your exit conditions. So what you do is you calculate the point that you're trying to calculate the distance to. So that is the current distance you have marched, added to your vector in the direction of the vector, and then you calculate the minimum distance. And in this is what's called the map function in these settings. So what it is here, it says signed distance to sphere from point P, the same point. And sphere is just a 4-dimensional vector. So the first 3 components is the position of the sphere, and the 4th is the radius. And the signed distance to the sphere is pretty simple. It's just the point, and you subtract the center of the sphere. You take its magnitude, and you subtract the radius, and that will give you a sphere. That's basically every point around the volume. And I have a plane. It's even simpler. That's just the y component of the p plus the height of the plane you're trying to do. So that will return, and I have this shade pixel that will just put red if it hits something. So that is that scene. So that is a sphere on a plane, but it's just a red mess at the moment, so we have to introduce some shading. So now we will do the same thing of calculating normals. When you're dealing with signed distance functions, you can't really do the polygon route with the cross product. So what you do is you shift your vectors a little bit in all directions, and you shift it by a little value, and you do the difference of those, and then you calculate the average of that into a new vector, and that gives you this normalized or normal colors on the sphere again. And this means that we are doing something right. Now we can start having some fun. Now we can implement some shading on this thing. So the first thing is we can do a get shadow. The shadow we get by just ray march in the opposite direction to the light. So that will give us a shadow. And what we can do here is we check the distance. And here we can calculate the same thing that we did with the Lambertian and all that stuff. So the same thing we can do, like check if it's aligned with the light. We can apply that as an attenuated color on the surface, and we will get the same shading. So that is essentially the same for the ray marcher and the ray tracer. And the next thing we can do is that we can figure out to give the objects different materials, and that's a bit different in this case. So what we have to do is we have to do this distance estimation twice. One, to get the distance we are marching to do the march. And once we hit something, we do that calculation once more. But this time, we just figure out which thing was the thing that we were closest to, and then we can return something representing that material. So in this case, if we're closest to the sphere, then we render the sphere. If we're closest to the plane, we render the plane. And then so now we have two colors. Now we can implement whatever we want. For instance, we can do some texturing. So I've implemented a simple checkerboard pattern for the plane. It's pretty simple. You just take the modulo of your coordinates, and I will give you one or the other. And that will result in this checkerboard pattern. The sphere, I have calculated the coordinates for the texture. So I take the point on the sphere, and I try and scale that into where along the sphere I am in normalized coordinates. And then I take a picture, and I look up a pixel that is that distance from the center of the edges of the picture, and I just pick that color, and I put that on the sphere. And that will just wrap that around like Christmas paper around the sphere. So I have shadows, I have textures. I can add some fancy lighting, so I can add a specular highlight. So that is basically a reflection vector towards the light. And and then you calculate the exponential fall-off gradient from that point along your surface, and then you get this nice highlight. So that is this. All this code is up, and I try to comment it as good I can, so if you're interested, you can check that out after the talk anyways. But now I have also added some real reflections. That is the same as it is for the ray tracer. Once you hit something that's reflective, you just march in the opposite direction. You do the whole thing again, and you shade it in. And you can do that for as many bounces as you want. But the cool thing about a ray marcher compared to a ray tracer is we only need one bounce to get that fidelity or reflection, whereas in the ray tracer, we would have thousands of bounces in order to get the same fidelity. So that is the ray marcher. And now I had that, and I was really eager to get back to work, to tell my colleagues about this stuff. And let's see if I can get this presenter view thing back. For some reason, I have to do it twice. So, armed with the ray marcher and the ray tracer and the rasterizer, I thought, well, they still weren't that impressed. So I didn't really impress my colleagues. But I did learn some valuable lessons. For instance, I did learn a hell of a lot about JavaScript, and I learned a lot about math that I didn't know from prior. And it turns out you could do this in JavaScript. You can do this, and you can do many other things in JavaScript, and I've done so since. You can create hardware emulators and compilers and software synthesizers and machine learning and much, much more, which is kind of fun. And it has given me more interesting weekend projects to do. And it did inspire me to learn more about GPUs and graphics and using GLSL. And it also, the thing that was so cool to me was that it also inspired my son to take up coding, because suddenly it wasn't boring enterprise software, it was graphics on screen. And it was really cool to bring my son this year to his first Demoscene party. So we went to a Demoscene party together. Who needs to take their kid fishing when you can take them to Demoscene parties? He's 15, and we actually won the competition. So we actually won the first prize in the demo competition with the demo we made together. And that was pretty cool. And this is the demo we made. I'm using everything I learned through this experience in this thing.
Escape.
Only thing is this is real time. I made it in WebGL instead of JavaScript, because it was real time.
Escape avoided.
So this is a nice effect that uses the frequencies of the sound to modulate the colors and the sine waves that go together to make this thing. So that makes it sync to the music.
Escape the singularity.
And this is fractals, and they are modulated by the sound again, the same for the coloring scheme. And the way you get these nice, cool organic shapes is you use something called orbit traps, which are these points that trap the exponential going to infinity parts into certain attractors, which create these nice organic shapes, which is kind of cool. So that was a couple of Julia sets, this is a Mandelbrot set, and of course, since we have made a ray marker, we need to extend this in 3 dimensions. So the next thing we do is we do that. No, sorry, we combine all the factors into one. Then we do it in 3 dimensions. So again, we're modulating the color space and the frequency of the
Escape the dimension.
And now we are doing it in 3 dimensions. We will end up finding a little landscape flyby in real time. And again, this is just using mapping coordinates. And we are flying through a wormhole. And this is cool thing about ray marking is that since you can get inside of objects, you can also calculate volumes. So this is like smoke and clouds that are mixed together. And we finish off in this really landscape. And through the course of doing this, I've actually made a library. So if you want to play with it, I have vectors, matrices, complex numbers, and shapes, and whatnot. It's in the NPM. It's called Dr. Circuit's Canvas library, if you want to play with it. Some people are playing with it. If you want to get up and running and creating these effects, I've created a Yeoman generator for both HTML5 graphics using the canvas and for WebGL if you want to get started in WebGL, which is also fun. I also have a talk and a workshop on that. Not on this conference, but a future conference. And the key takeaway I want you to take is that you can actually do this with JavaScript. And you may ask yourself, why on earth would you do this and give yourself these constraints and build the wheel all over again? Well, the one thing I want you to take away is that if you want to learn about wheels, it's okay to reinvent them. And that's all I had. Thank you. These are my things if you are interested. And if there are any questions, I will gladly answer them. Yeah, thank you. Questions? Cool, thank you.